sklearnmetricsclusterpairconfusionmatrix. Description: the pair confusion matrix function calculates the confusion matrix for each pair of clusters in a given clustering result. It compares the predicted cluster labels to the true labels, providing a detailed view of the performance of each cluster in terms of correctly and incorrectly classified instances. This function is helpful for evaluating the quality of a clustering algorithm and identifying clusters that might require further refinement. Inputs: labels true A1D array representing the true cluster labels for each instance. Label spread A1D array representing the predicted cluster labels for each instance. Outputs: confusion matrix A3D array where each 2D slice represents the confusion matrix for a specific pair of clusters. The shape of the array is n clusters. N clusters. 2. Where n clusters is the number of clusters. Steps: the function iterates through all possible pairs of clusters. For each pair, it creates a 2x2 confusion matrix based on the true and predicted labels of the instances belonging to those clusters. The resulting confusion matrices are then stacked into a 3D array. Metrics: precision: the proportion of correctly classified instances within a given cluster. Recall: the proportion of true positive instances within a given cluster that were correctly classified. F1 score: the harmonic mean of precision and recall, providing a balanced measure of performance. Visualization plots: heat map: a heat map can be used to visualize the confusion matrices for each cluster pair, showing the distribution of instances across the true and predicted labels. Confusion matrix plot: a separate confusion matrix plot for each cluster pair can provide a clear and detailed view of the classification performance. Fine-tune parameters: none. Uncertainty methods: none. Challenges and fixes. Challenge 1: imbalanced clusters. When clusters have significantly different sizes, the confusion matrix can be skewed, making it difficult to assess the performance of smaller clusters accurately. Sample use case that resulted in challenge 1: in a clustering scenario with a small cluster of outliers and a large cluster of typical instances. The confusion matrix might show a low precision for the outlier cluster, even if it correctly classifies all its instances. Fixes to challenge 1: use weighted metrics. Employ metrics like weighted precision and recall that account for the class imbalance. Resampling techniques. Apply techniques like oversampling or undersampling to balance the class distribution. Cluster-specific evaluation. Evaluate the performance of each cluster separately, considering the specific characteristics and size of each cluster. Challenge 2: sparse confusion matrices. When the number of clusters is large, the confusion matrices for specific cluster pairs can be sparse, resulting in unreliable metrics. Sample use case that resulted in challenge 2: in a clustering with a large number of clusters. The confusion matrix for a specific cluster pair might contain only a few instances, leading to high variance in the calculated metrics. Fixes to challenge 2: aggregation. Aggregate confusion matrices for similar clusters to improve the statistical significance of the metrics. Thresholding. Apply a threshold to filter out cluster pairs with too few instances, focusing on the most populated and informative pairs. Ensemble methods. Utilize ensemble clustering techniques to create more robust and consistent clustering results. Mitigating the effects of sparse confusion matrices.